These organic molecules might look quite similar at first glance. However, if we add bromine water to each of them, only some would decolorize it. But why only some? Well, the answer lies in how we classify organic molecules, and that's what we're going to be looking at in this lesson. We'll cover what functional groups are and why they're important in organic chemistry, what a homologous series is and the key characteristics each member of a series has, before finally exploring each of the main homologous series that you need to be able to identify in Year 12 organic chemistry. And if you'd like to follow along with this lesson, there's a free Learn Pack containing guided notes, worked examples and practice questions linked below. So let's start with the key idea that everything in this topic is built around: functional groups. Functional groups are specific atoms or groups of atoms within a molecule that determine its characteristic reactions. If a molecule contains a particular functional group, it will react in a particular way. If it doesn't, then it won't. And that's why only some of the molecules you saw earlier would react with bromine water. Now, there are literally millions of different organic compounds, making it all but impossible to study and learn about each one individually. So instead, chemists use a system to organise them based on the functional groups that they contain. Molecules with the same functional group are collected together into families, and as cute as that sounds, we actually call these families homologous series. Now, odds are you've already come across some examples of homologous series, such as alkanes, alkenes, and alcohols, with each being defined by the functional group all molecules within that series contain. So a homologous series is a group or family of chemicals that all contain the same functional group. As a consequence to this, each homologous series has several key characteristics. The most obvious one is that each member of a particular homologous series will contain the same functional group. And because of this, each member will have similar chemical properties and therefore react in a similar way. Every member of the homologous series will have the same general formula, and consecutive members will differ in chain length by CH2. Finally, members of a homologous series will display a trend in physical properties. For example, their boiling point may increase as the carbon chain length increases. In the past, exam questions have only ever asked you to identify two characteristics, but sometimes they give you one as an example and then ask you to state two others. To be on the safe side, I would encourage you to learn three characteristics of a homologous series. Personally, I'd recommend the three I've highlighted on screen, as they're distinct from each other, but not too wordy. So we've seen how organic molecules are classified into homologous series based upon the functional groups they contain, and how each homologous series has a particular set of characteristics. Now we can start to apply this system by looking at the main homologous series you need to know in Year 12 chemistry. For each one, we'll name the homologous series, identify the functional group it contains, give the general formula, and finally look at being able to identify it from the names of compounds by considering the prefixes and suffixes used. We'll start with the simplest homologous series, alkanes. Alkanes are a homologous series of organic molecules that only contain single bonds between carbon atoms. Therefore, the functional group present in all alkanes is a carbon-carbon single bond. The general formula for alkanes is CnH2n plus 2, and this tells us that for every carbon atom, there are twice as many hydrogen atoms plus 2. This also tells us that alkanes are hydrocarbons, compounds containing carbon and hydrogen atoms only. Alkanes are named using the suffix ane, and here we have an example of propane. We can clearly see from the displayed formula that it only contains single bonds between carbon atoms. We can also clearly see the ane suffix in the name of the molecule, identifying that this molecule is an alkane. Next up we have alkenes, another relatively simple homologous series. This time each member contains at least one carbon-carbon double bond, making a carbon-carbon double bond the functional group for alkenes. Alkenes have the general formula CnH2n, telling us that for every carbon atom, there are twice as many hydrogen atoms. And again, this shows us that alkenes are hydrocarbons, as they too only contain carbon and hydrogen atoms. Alkenes are named using the suffix ene, and this time I have an example of but-1-ene. Now don't worry too much about why I've got a number in there at the moment, that will be covered in a separate video on naming organic compounds. But the key thing is that we can clearly see the functional group, the carbon-carbon double bond, as well as the suffix ene shown in the name. Next up is cycloalkanes, and as you might have guessed from the name, cycloalkanes are closely related to alkanes. However, instead of forming straight or branched chains, the carbon atoms are joined together to form a ring-like structure. Like alkanes, cycloalkanes only contain single bonds between carbon atoms. Therefore, the functional group present in cycloalkanes is a carbon-carbon single bond. The general formula for cycloalkanes, however, is CnH2n. Now, you might recognise this as the same general formula we saw earlier for alkenes. This highlights an important point. You cannot always identify a homologous series from its general formula alone. You must consider the functional group present within the molecule. Cycloalkanes are named using the prefix cyclo and the suffix -ane. And here I've got an example of cyclohexane. We can clearly see that the carbon atoms are arranged in a ring and that all of the bonds between carbon atoms are single bonds. We can also see both the cyclo prefix and the -ane suffix in the name, showing us that this molecule is indeed a cycloalkane. Now let's move on to halogenoalkanes, or haloalkanes as they're sometimes called. Halogenoalkanes are also closely related to alkanes. In fact, they are just alkanes that have had one or more hydrogen atoms replaced with a halogen atom. The functional group present in halogenoalkanes is therefore a carbon-halogen bond, shown as CX, where the X represents a halogen atom such as fluorine, chlorine, bromine, or iodine. The general formula for halogenoalkanes is often given as CnH2n+1X. However, this assumes that only one hydrogen atom has been replaced with a halogen. In reality, several hydrogens could be replaced. Halogenoalkanes are named based upon which halogen atoms are present, and we use the prefixes fluoro, chloro, bromo, or iodo depending upon which halogens are in the molecule. Here we have an example of 1-bromopropane. The carbon-bromine bond is easily seen within the displayed formula, and we can see the bromo prefix in the name. And now moving on to a potentially familiar series, alcohols. The functional group for alcohols is the hydroxyl group, and all alcohols contain at least one hydroxyl group but can contain multiple. The hydroxyl group is simply an OH group attached to a carbon atom. The general formula for alcohols is therefore CnH2n+1OH. But again, this assumes that the alcohol only contains one hydroxyl group. Unlike the homologous series we've looked at so far, alcohols are named using either a prefix or a suffix. Sometimes alcohols are named using the suffix -ol, but they can also be identified by the prefix hydroxy. When each of these is used is dependent upon what, if any, other functional groups are present, and this will be covered in more detail in the video on naming organic compounds. Here I've got the example propan-1-ol. We can see the hydroxyl group present at the end of the carbon chain, and as it's the only functional group present apart from alkane carbon-carbon single bonds, we use the suffix -ol. Now let's take a look at a new series, aldehydes. Aldehydes are a homologous series of organic molecules that contain a carbon-oxygen double bond at the end of a carbon chain. The functional group present in aldehydes is therefore CHO, and the general formula is CnH2nO. Aldehydes are all named using the suffix -al, and here we have an example of propanal. The carbonyl group, or the carbon-oxygen double bond, is at the end of the carbon chain, and we can also tell from the suffix -al that this is an aldehyde. And our next series, ketones, are very similar to aldehydes. Like aldehydes, ketones contain a carbon-oxygen double bond. However, in ketones, it's located within the carbon chain rather than at the end. The functional group present in ketones is therefore a carbonyl group, represented as CO, but you'll often see Rs joined to either side of the carbon atom. These Rs represent alkyl groups, which is just a fancy way of saying carbon chains, and they are there to indicate that the carbonyl group is located somewhere in the middle of the chain and not at the end. The general formula for ketones is CnH2nO, which is identical to the general formula for aldehydes, once again highlighting the importance of looking at the functional group and not just the general formula when identifying a homologous series. Ketones are named using the suffix -one, and here we have an example of propanone. The carbonyl group within the carbon chain is clearly visible, and the name features the suffix -one. And now carboxylic acids. Carboxylic acids are weak acids that contain a carboxyl group, which means that carboxylic acids contain the COOH functional group. Carboxylic acids have the general formula CnH2n+1 COOH and are named using the suffix oic acid. As an example, we have propanoic acid. The carboxyl group is clearly visible within the displayed formula, and the suffix oic acid confirms that this molecule is a carboxylic acid. Next, we're going to have a quick look at nitriles. Although nitriles are not a homologous series you'll study in detail until year 13, you are expected to be able to recognise them and name them in year 12. Nitriles are compounds that contain a carbon-nitrogen triple bond, and so the functional group present in all nitriles is therefore CN. You don't need to worry about the general formula for nitriles, as they can get a little bit complicated and aren't examined as part of the course. Nitriles are named using the suffix nitrile, there's nothing too complicated there, and here we've got the example propane nitrile. The carbon-nitrogen triple bond is visible at the end of the carbon chain, and the suffix is present in the name. The final homologous series we need to look at is amines. Amines contain an amino group and so have NH2 as their functional group. As with nitriles, the general formula for amines goes beyond the scope of what you need to know for A-level chemistry and actually depends upon the type of amine you have. Like alcohols, amines can be identified using either a suffix or a prefix, depending upon what other functional groups are present. Sometimes amines are named using the prefix amino, and other times they are named using the suffix amine. Here we've got an example of propan-1-amine. The amino group is present within the displayed formula, and the suffix amine in the name. So in summary, what we've really done in this lesson is start to organise organic chemistry. Instead of treating molecules as individual cases, we group them into homologous series based upon functional groups. Once we do that, we can start to predict how whole families of compounds behave, recognise repeating patterns in structure, and use general formulae to describe them. This gives us a structured way of thinking about organic chemistry rather than trying to learn every compound separately. In the next lesson, we'll move on to nomenclature, how we name organic compounds using systematic rules based on their structure and functional groups. And if you'd like to continue with the course, the full Introduction to Organic Chemistry playlist is on the screen now.